What's up, guys? Long time no see. It's about time we get busy again with some trig. I hope you have the two lessons we've already covered. I put a new assignment sheet up, so you should be able to follow along with me. But right now we're on April 6th, and we're going to start taking a look at the unit circle, how to use it, which is the biggest thing. I think a lot of people just teach the unit circle and call it a day, but we're going to learn how to use it and make our life a little bit better, a little bit more efficient with solving trig values for special angles like 30, 60, 45, a lot of the ones that you'll see on the unit circle. So without further ado, let's take a look at the unit circle and what it means, and maybe learn some tricks for setting it up. Okay, so I'm looking at the unit circle. You can find this on page 13 in the book. And at first glance, if you haven't seen this before, it looks kind of a mess. It's giving you all kinds of, it looks like coordinates right here. It looks like you've got angles measured in both degrees and in radians, and you can see that all the way across. But at first glance, it seems like a lot to memorize. Might be a little bit too much. So what I want to do is kind of walk you through the whole general idea of what this is. And then once we do that, hopefully you'll kind of see it a little bit more clearly and have a better idea what's going on. Okay, so if you remember from geometry, we really were dealing with all kinds of different triangles, but three specific triangles we call special triangles were the 30-60-90 triangle, the 45-45-90 triangle, and the 60-30-90, which is really like the 30-60-90 just turned over on its end. But they all have these same ratios. And like we talked about the first day of trig, trigonometry is really just a study of ratios. And that's all the trig functions mean. A trig function of 30 will always mean that value. I mean, if you have the sine of 30, it will always mean that value over that value. That's the ratio. If you had something like the tangent of 60, it'll always be that value over this value because of those ratios that we defined earlier. Well, on these, you know, and you talked about this in geometry, we used the value of A to show that there was a proportion there. It wasn't always a length of 1 and a length of 2. Like, for instance, I could triple all of these, and I could have a 3 and a 6 and a 3 root 3. A, for instance, could be equal to 5 in all of these. It could be 5 and 10 and 5 root 3, and that's true for all three of these. So what I want to think about is, since we are going to have ratios of these two sides, and since the two sides you'll be putting like opposite over hypotenuse or adjacent over hypotenuse or whatever, if you think about it, it's kind of like this A is not there once the ratio is taken. And if I don't think about the A and I just think about the sides, it might be a little bit more clear how we can take these triangles and place them in this unit circle. So the reason we call it a unit circle is because it has a length of 1. As a radius. So when you look at the unit circle, all of these triangles are going to be placed into the unit circle, and I'll show you this in a second. But what that means is the length of the radius will be 1. Well, you can see on ours, and you'll see this in a moment, this value, the hypotenuse, ends up being the length of the radius on all of them. Well, I don't want it to be equal to 2 or even to root 2. I need them all to be equal to 1. So what I'm going to do is I'm going to divide this by a 2 and that by a 2 and that by a 2 on this 30-60-90 as well as this 60-30-90. And when I do that, you can see the radius, 2 over 2, becomes a length of 1. Now, these two legs change size as well. So this is basically half that length, and this is this short leg here times root 3 ends up being that length. But these are the proportions of every 30-60-90 that will show up in your unit circle. And the same thing here. Here where 2 over 2 is 1. All right, these sides now have changed, and I know that the actual length didn't shrink down, but pretend they did. So this triangle has shrunk from a length of 2 now to a length of 1, and we're going to place these two proportions in for every 30-60-90, every 60-30-90 in the unit circle. Now for this one, I can't divide by 2. I would divide by root 2. I was about to ask you guys a question, but I'm realizing that you can't really answer. So root 2 over 2 is equal to 1. And then I have these two legs, 1 over root 2. Now in Algebra 2, pre-cal, we like to rationalize. So this is going to become a root 2 over 2. And this is going to become a root 2 over 2. And you remember how to do that if I multiply the top and the bottom by root 2 and simplify. So now we have new values or new proportions. Now, they're technically the same. They just look differently than they did before. But we have these proportions, and we're going to take these and put them into the unit circle. Okay? So I'm going to slide over my unit circle just to kind of demonstrate this. So right here, you can see this unit circle, and you can see when we're looking at this right here, this right here, if I draw a line down, that represents a 30, 60, 90 triangle. This would be 30 inside here. This would be 90. This would be 60. So 30, 60, 90. This also shows up again here. There's another 30, 60, 90. It shows up here as a 30, 60, 90. And it also shows up here as a 30, 60, 90. Now, I'd love to start drawing all these angles in and all these values in, but by the time I started labeling all of the 30, 60, 90s, the 45, 45, 90s, and the 60, 30, 90s, not to mention the angles at 0 and at 90 and at 180, etc. By the time I am done with all of this, it would be a mess. So what the unit circle does is it takes these values, and because we already know the hypotenuse is 1, I'm going to take this movement here, this long leg and this short leg, since they end up being coordinates. Think about this as a big x-axis and a big y-axis. This is like my x-coordinate and my y-coordinate. So you can see that. I'll bring it back. All right, here was my original 30, 60, 90. So instead of labeling this root 3 over 2 and that a half, I'm going to label this point square root of 3 over 2 and 1/2. And you can see that right there. So these coordinates represent those points, but they really stand for the sides of the triangle right here when that's 30. And then instead of writing 30 and 60, I'm going to be saying, okay, a 30-degree reference angle, that's why that's 30, has these proportions. All right? And same thing over here. If I come over to the left in the second quadrant, that value right here is 150 degrees. And we'll talk about that in a second. That's 150 degree. That basically is moving all the way over to here. But I can represent any trig value of 150 using these same legs. Now this time, instead of going to the right square root of 3 over 2, I went to the left square root of 3 over 2. Well, that's negative movement, but I still went up 1/2. So I'm labeling that negative square root of 3 over 2 and 1/2. You can see down here at this 30, 60, 90, right? If it's 180 all the way to there, it's 30 more. This is another 30, 60, 90. And you can see, I really don't want to write in there 30 because it's really 30 plus this 180. So what I say is, at that spot right there, it's 210 degrees. Now, it could also be negative 150 if I came around from the negative side, but let's just focus on the 210. But to get to that point, I'm going to go left square root of 3 over 2, down 1/2. Okay, and then back over here to the fourth quadrant, I could think about this as a negative 30 degrees, or I could go all the way around to 330. Notice they put both of them right there. If you're ever filling one out, you can use, I probably just use the positive for now, but you can think about it both ways. But again, the movement, positive to the right, square root of 3 over 2, but this time down, so a negative 1/2. So you can see on all of these 30, 60, 90 values, or triangles, I've listed the coordinates and then the angle. Now the radian measure is important also. So notice I put pi over 6, that's what 30 degrees is, but we're going to talk about more about how to, a clever way of memorizing those if you're having trouble knowing, so that you don't have to convert them each time. So for now, just focus on the degrees. Now, I can do the same process with 45 degree angles. Look right here. This is a 45, 45, 90 if I look at that triangle outlined by this. But again, I'm not going to put all the angles in here because it starts to get really combobulated with everything, but I'm going to use what I know about a 45, 45, 90. Remember, if I go back to what I learned about a 45, 45, 90, right here, I'm going to be going to the right, square root of 2 over 2, up square root of 2 over 2. And remember, the hypotenuse is still 1. So going back to this, if I think about it, I'm going to the right, square root of 2 over 2, up square root of 2 over 2. Those are my coordinates. And I honestly hate the way they write those with little, I like writing it the root 2 over a 2 and root 2 over a 2, and I hope you guys do the same. But anything I need to know about a 45-degree angle, those are my x and y coordinates of that point, and this is really going to come into play. Now again, that 45, 45, 90 shows up here. Well, look, it shows up there too. Right? There's over 45. 45-degree angle would be this right here. So that side and that side are the same, and I'm listing them, but I got to make this negative because I'm going left and then up, right? And again, that would be 135 degrees, because if it's 180 all the way to here, and I subtract that 45, that puts me at 135. All right. Now I can also see these 45, 45, 90s down here in the third quadrant, and also over here in the fourth quadrant. And notice the coordinates, root 2 over 2, root 2 over 2, negative root 2 over 2 to show that I went left, but then up root 2 over 2. And then down here, negative root 2 over 2, but then down negative root 2 over 2 to show left and down. And then over here, to the right root 2 over 2, but down root 2 over 2. That's why that's negative. So you can see the 45s show up as well. Now, with the same thing in mind, here are your 60, 30, 90s. There's a 60, 30, 90. There's a 60, 30, 90. There's a 60, 30, 90. And there is a 60, 30, 90. So, and those have the same coordinates as the 30, 60, 90, except they're switching the order. Instead of going like back to the 30, instead of going over a whole bunch, square root of 3 over 2, and then up a little bit of half, now you're going over a half, but then up square root of 3 over 2. Negative a half, up square root of 3 over 2. Negative a half, down square root of 3 over 2. So that's negative as well. And then finally, positive a half, negative square root of 3 over 2. So anytime you go to the right or up, it's positive. Anytime you go left or down, it's negative. And those are all of our coordinates of these special triangles. Now, we really don't probably need a whole lot of specialness to figure out the coordinates of that, because again, the radius of a unit circle has a length of 1. So here I'm just going over 1 and then up nothing. So 1, 0. So at 0 degrees, which is also 360 or 720 or a number of ones that go around and around. But at 0, I'm going over 1, up nothing. At 90 degrees, I'm going left nothing but up 1. So 0, 1. At 180 degrees, I'm going left 1, up nothing. And then finally at 270 or negative 90, 270, I'm going left and right nothing, and then down 1, so negative 1. So those are our coordinates of everything. And I think you'll notice that the only coordinates that actually show up on this, there are 5. You have the biggest movement, which is 1, okay? And that shows up going far right, far left, up and down. You also, I'm going to say plus or minus 1, okay? You also have the square root of 3 over 2. That shows up, and that shows up on your long movements that go along with 1/2. So over square root of 3 over 2, up a half. Or maybe over a half, up square root of 3 over 2. So that next longest length, and again, it could be plus or minus. Then you have the next longest length is the root 2 over 2. You see that with anything that ends in a 5, basically. 45, or that's on the unit circle and ends in a 5. 45, 135, 225, 315. All of these have the root 2 over 2. Okay, and you'll notice that those always go in conjunction with another. So if I'm moving left that amount or right that amount, I'm going to be going up or down that amount. They always go together. And then also you have the second smallest movement. Technically the smallest one is nothing. And that's up a half, down a half, or maybe over a half to the right or left a half. So plus or minus 1/2. And then finally you could move nothing. But when you look at it, it really they're just 5 values that show up on the coordinates of your unit circle. And remember, all of these represent sides of your triangle. They're just sides, okay? And sometimes it's not a triangle. I realize it's hard to see 0 degrees as a triangle or 90 degrees as a triangle, but I hope that you can see that all of these points here represent angles that show up. They are a result of unit circle values that show up in special triangles. And all of these, if you think about their sides as coordinates, it's really going to help you with your trig identities. With your evaluating trig functions really soon. Okay, so remember, those are the only 5 values that are going to show up on your unit circle for your sides. Now, what's really important to remember is sides are basically coordinates. This is an x coordinate, that's a y coordinate. This is an x coordinate, that's a y coordinate. This is an x coordinate, that's a y coordinate. All of these are x's and y's. And if you remember, every one, I'm not going to do it on all of these, but all of these are a bunch of coordinates. And if you remember our trig functions, I can define trig functions a couple of different ways, okay? I can define them in terms of like opposite and adjacent and hypotenuse, but I can also define them in terms of, like, for instance, sine. Say sine of this 30-degree angle. We would normally say opposite side over the hypotenuse. Well, the opposite is the y, right? That's the y movement. So instead of saying opposite over hypotenuse, I'm going to say y over the radius. And the radius is 1. So the sine value ends up being just the y over 1. Well, if I want to find the sine of 30 then, right here, I can just go grab the y coordinate at the unit circle at 30 degrees, and I know that the sine... Okay, so this is a copy of the unit circle. It's on page 11 in your book, and I'm just going to walk you through how to fill this out, say on a test or whatever. Hopefully you're going to know this well enough that it'll be burned into your brain, but if not, you could sketch one out quickly and use these to answer a lot of the trig questions that you have. Again, my hope is that you don't have to sketch it, but you can think. But this is going to help organize your thoughts, I think. So initially, there are a couple things that we know that are going to help us. One is we know that if we go entirely around the unit circle, it's 360 degrees. So if I begin here at 0 degrees and I go all the way around, it's 360. So here I'm going to put 0 degrees, but just so you know, it's also equal to 360. Technically, I don't even have to go around that way. I could go the negative way. It could be negative 360. I could go around twice. It would be positive 720, but all of these values I could use in that position. But I'm going to write 0 degrees for now. Now, if all the way around is 360, then it should make sense that just halfway around would be 180. So I'm going to write 180 degrees there. Okay? Now, the reason why I'm about to do what I'm doing is because I'm trying to fit in the 30, 60, 90 measurements. So any angle that's a multiple of 30, like 30 or 60 or 90 or 120, I want to have coordinates, and we've talked about the coordinates. I want to have the coordinates of those so that I can use those x's and y's to evaluate my trig functions. So first thing I'm going to do is take that 180 and divide it up into 6 parts. Okay? Now if you think about 6 parts, if I split it in half, that would be right here. So 180 divided by 2 gives me 90, right? And then if I split 90 up into thirds, that would be there and there would give me that angle, or that part right there, that part right here, and this part right here. So if I split 90 up into thirds, that would make this first one 30 degrees. Skip that middle one because that's breaking 90 into a half. So that would be 30. If I split it up right there into thirds, that would become a 60-degree angle. And you can kind of see 30, 60, 90. Well, if I continue that, if this is 30 and that's 60 and that's 90, well, this would be another 30, which would be a 120. Skip over this. This would be another 30 to get me to 150. This would be another 30 to 180. And if I continue this around, that becomes a 210. Skip this one. Another 30 becomes a 240. Another 30 becomes a 270. another 30 becomes a 300, and then another 30 becomes a 330, and then another 30 brings me back to where 360 and where the original 0 is located. And again, that's breaking 180 into 6 parts. 1, 2, 3, 4, 5, 6. 180 divided by 6 is 30, and that's why I began with 30-degree increments there. Well, if I did the same thing again and said, what if I broke 180 into 4 parts? Breaking it into 4 parts would be like breaking it in half to give me 90, and then breaking that in half again to give me a 45. And that's why that's a 45. Well, if I'm jumping every 45 degrees, first to 45, add another 45, I get 90. Then if I added another 45, I'm now at 135. If I add another 45, I'm at 180. Add another 45, I'm at 225. Add another 45, I'm at 270, which I already have filled in. Add another 45, I'm at 315. And if I add another 45, I'm at 360, which is back to my original 0 location. So those are the degree measures of all of these. And you can see I have them all filled in now. Now these are the positive movements. So that's positive 30, positive 45. If I were to go in a negative direction, this would be a negative 30. So that's why on your other unit circle, they will have a 330 right there, and they'll have it equal to negative 30 as well. Or they'll have that 315 equal to negative 45 as well. Because if I move in a clockwise direction, I get the negative angles. All right. And the other unit circle has that, but hopefully as we move through this, this will continue to make more sense. So these are our degree measurements right here. And then now I want to talk about radians. Well, we talked earlier that 360 degrees was the same thing as 2 pi radians. Again, 2 pi is about 6.28. And if I took a radius at length and I laid it across a circle, I would get about 6.28 lengths of the radius around this. So anyway, right here, I can call that 0 radians, which I will, but I could also call it 2 pi radians because 2 pi goes with 360. Okay, so if that's 0 radians, if that's also 2 pi, then halfway around would be pi radians. Okay, now I'm going to do the same thing to pi that I did with 180. If I divide pi into 6 parts, each part would be pi over 6. So that means there's 1, 2, 3, 4, 5, 6. So think about it like 6 slices of pi. Well, that first angle is 1/6 of pi. So it is 1/6 of pi, or pi over 6. All right. Well, if that's pi over 6 and I add another pi over 6 to it, I get 2 pi over 6. But I want to simplify that. So I simplify 2 pi over 6 into pi over 3. Well, if I add another pi over 6 to that, I take the 2 pi over 6, add another pi over 6, I get 3 pi over 6. Well, that's the same thing as pi over 2. And I'm going to show you a trick on memorizing these in a second. And if I take that 3 pi over 6 and add a pi over 6, I get a 4 pi over 6. But that 4 pi over 6 simplifies to 2 pi over 3. But if I take that 4 pi over 6 and add another pi over 6, I get a 5 pi over 6. And if I take that 5 pi over 6 and add a pi over 6, I get a 6 pi over 6, which is pi. Okay, now keep going. Add another pi over 6, and I get 7 pi over 6. All right, add another one. Remember, I got to skip this one right here. And I get to 8 pi over 6, which is 4 pi over 3. Add another pi over 6, and I get to 9 pi over 6, which simplifies to 3 pi over 2. If I take the 9 pi over 6 and add a pi over 6, I get to 10 pi over 6, which is 5 pi over 3. And then if I take the 10 pi over 6 and add a pi over 6, I get to 11 pi over 6. And then finally, an 11 pi over 6 plus a 1 pi over 6 is a 12 pi over 6, which is 2 pi, and we're back to where we were. All right? So all of these 30, 60, 90s, I have all filled in now, all the way across. So to deal with the 45-degree angles right here, I've got to do the same thing. To deal with the radian values at 45 degrees, I have to do the same thing I did before. So I'm going to take that pi and divide it by 4. Dividing it by 4 gives me 1, 2, 3, 4 sections right there. Okay, so the first one would be 1/4 of that pi. So pi over 4. If I add a pi over 4 to that, I get 2 pi over 4, which jumps me to this. It's already simplified. If I add a pi over 4 to 2 pi over 4, I get a 3 pi over 4, which jumps me right there. Add another pi over 4, 4 pi over 4, which is pi simplified. Add a pi over 4 to 4 pi over 4, and I get 5 pi over 4. Add another pi over 4, 6 pi over 4, that's simplified. Add another pi over 4, 7 pi over 4. And finally, if I add another pi over 4, I get 8 pi over 4, which is the 2 pi. And there are all my unit circle values for the degrees and the radians filled in. All right, the last thing I want to do is fill in these coordinates. And once I have the coordinates, I'm home free when it comes to using this. Now, we've already done this. If you think about it, what did I say earlier? I said the only movements that you ever end up having on this unit circle are either plus or minus 1, plus or minus the square root of 3 over 2, plus or minus root 2 over 2, plus or minus 1/2, or 0. And the 1 and the 0 always go together. The square root of 3 over 2 and the 1/2 movements always go together. And whenever you have a root 2 over 2, it's both the x and the y movement. Now, if you think about this as being the biggest movement, plus or minus 1, and 0 being the smallest movement, then the other two, think like this. I think of this one, since it's a little bit bigger than the other two, as a lot. So a lot of movement. All right, this is me kind of helping you think a little bit. The 1/2 is the smallest of the three. So I think about this as a little movement. And then because this occurs with both x and y, I think about this as same movement each way. Okay? So think about this as I'm coming up with these coordinates. So I'm going to start with 0 because that seems pretty easy. I'm going over 1 and up nothing. So 1, 0. Now, this coordinate, remember, this right here is a 30, 60, 90 triangle. And this is the big leg of the triangle, which is a lot of movement followed by a little movement. So remember, a lot of movement to get to there is like doing square root of 3 over 2. And since I went to the right, it's positive. And then I went up a little movement is a 1/2. All right? Now, for the 45, 45, this is a 45, 45 degree, 45, 45, 90 triangle. That's the same movement each way. And remember, same each is the root 2 over 2, root 2 over 2. Now, this is a 60 degree angle right there. So that's a 60, 30, 90 right there. And that's a little followed by a lot of movement. So a little over, a lot up. A little, a lot. Remember, a little movement's a half, a lot of movement is square root of 3 over 2. And these are all positive because I'm either going right or up. Now, straight up, I went nothing left or right, and then up 1. Now, when I get into the second quadrant, I'm going left on each of these. Every time I go left, it's got to be negative, but I am moving up, so it should be negative, positive coordinates. What's this first one at 120 degrees? A little, a lot. So a little, negative 1/2, a lot, square root of 3 over 2. What's this next one? This 135 degrees? 135 degree angle, remember, comes from here all the way over, but it's created by a 45, 45, 90. So these two sides are the same, right? And anytime I do the same movement each way, square root of 2 over 2, square root of 2 over 2, except I'm going left, so negative root 2 over 2, but then up, positive root 2 over 2. And then finally, this 150 degree angle right there, I'm moving over a lot and then up a little, so left, negative, a lot, square root of 3 over 2, and then up, positive, a little. And then finally, left 1, but since left is negative, negative 1, up nothing, 0. And that's the unit circle just over and over again. So I'm going to go ahead and fill in the rest of these, but a little bit more quickly. Each of these movements, I'm going to go over and I'm thinking either a lot, a little, or same, and I'll kind of walk you through it. So left a lot, negative square root of 3 over 2, down a little, negative 1/2. Left and down the same, so negative square root of 2 over 2, negative square root of 2 over 2. and then left a little, negative a half, down a lot, negative square root of 3 over 2, and then straight down, negative 1, left and right, nothing, 0. And then here in the fourth quadrant, I'm back to moving to the right, so all of the x coordinates will be positive, but I'm still going down, all the y's will be negative. So right a little, down a lot, negative square root of 3 over 2. Same, so positive square root of 2 over 2, and then negative square root of 2 over 2. And then finally, over a lot, down a little, positive square root of 3 over 2, negative 1/2. And there's my unit circle. And why do I want this? Well, remember, these are all coordinates, x's and y's. And my trig functions are defined in terms of x, y's, and r's. And on this unit circle, what's the r value every time? 1. That's the key to the unit circle. It always has an r value of 1. So if I know that, now I can simplify my unit circle. I can simplify trig functions of unit circle angles just by reflecting on these coordinates. Because sine, think about it, sine of any angle is the y value over the r. But if you're using the unit circle and the r is 1, it just ends up being the y value. For instance, cosine of any angle is the x over the r. But again, if the r value is 1 on these, then it ends up being just the x coordinate. Tangent. Tangent is defined as the y over the x. Well, that doesn't have a r value, so that doesn't come into play, but I would just take the y coordinate at that angle and put it over the x coordinate and simplify. And all the trig functions are done similarly. So what I want to do now is I want you to turn back to your to page 13 or over to page 13 and take a look at these. So picking back up on page 13, notice I've got all the trig functions defined over here in terms of their old school definitions and also in terms of y or r. But remember, if I'm going to use the unit circle, which I'm hoping to do, rather than draw pictures of every possible angle and labeling them old school ways like we did with the geometry, I'm going to think about them using these unit circle values, which means any trig function that has an r value in it, which is all of them but tangent and cotangent, I'm going to think about the r value as 1 and just use the y and the x coordinates. So let me walk through a couple of these. Like sine of 120. We know that 120 is right here. And the sine of 120 is equal to y over r. Again, r is 1. So all I need to do is grab the y value, which is square root of 3 over 2, and that's what the sine of 120 simplifies to. And again, that would be the ratio of the two sides of a triangle if you were using 120 as its angle. All right, when you get to cosine of 7 pi over 4. Now, we've already labeled this unit circle. And remember, 7 pi over 4 is way down here, okay? And I'm still going to show you some of the tricks for filling this thing out. But 7 pi over 4 is way down here. And if you think about 7 pi over 4 that came from that right there, I can use its coordinates to answer any questions about a trig function at 7 pi over 4. So we know that cosine is defined as x over r. And since we're using the unit circle and r is 1, the cosine of that is just the x coordinate at 7 pi over 4. So I can just grab root 2 over 2. That's what 7 pi over 4 is. Pretty simple. If you look over on page 14, I've got a few more for you. On page 14, look at the tangent. Tangent of 210. Okay, so if you look at 210 degrees, so flip back. I can't put both of these on the screen at once. But if you look at 210 degrees, you'll see that the y value of tangent is negative 1/2, and the x value is negative square root of 3 over 2. So because tangent's defined as y over x, I put that y over that x. Now, what I didn't show you is me multiplying through by the reciprocal. So remember, to divide by a fraction, you multiply by the reciprocal. The 2's end up canceling, and the negatives end up canceling, leaving me just the 1 over root 3, which I can rationalize. Okay? And I'll talk about memorizing these later, but I have all my tangent values memorized. It's just much simpler in the whole scheme of things. But for now, do this. All right, cotangent of 225. we define cotangent as x over y. Well, all I got to do is go find 225. So when you go find it, what do you see as the x coordinate? Negative root 2 over 2. What do you see as the y coordinate? Negative root 2 over 2. And that's really easy. They both cancel and leaves me a value of 1. Okay? All right, and then what about secant of 855? Well, secant of 855 is a little trickier because 855 is not on my unit circle. Evidently, I've rotated more than one time around. So evidently, maybe I've gone around once or twice or 3 times to get to a value that big. So what you have to do to get to an angle that'll make sense for you is go ahead and start subtracting 360 from that 85. And you can see here I had to do it a couple times until you recognize the angle. And when I recognize that angle, I'm going to use the values at 135 to answer my questions about secant. Now, we know that secant is equal to r over x, but remember, r is 1. So a secant is just the reciprocal of your x value there. So what I do for secant of 855 is I'm going to use 135 in its place. I'm going to take 1, I'm going to divide it by the x value at 135 degrees. So when you go to 135, you look at the x value, you see that it is negative root 2 over 2. Now, I did this. To divide by a fraction, I multiply by the reciprocal. But really, if you know that cosine of 135 is x, the secant is just the reciprocal of that x. And you can see that right here. So just take the x value and flip it upside down. And that gets me right here. Okay? And then I can rationalize again. That root 2 and root 2 gives me a 2, which then cancels, and I'm left with a negative root 2. Now, this is probably the trickiest of all of them. Cosecant of 22 pi over 3. Clearly, 22 pi over 3 is way bigger than 2 pi. It's like, what, 7 and some change pi. So we need to get rid of all those extra rotations of 2 pi, kind of like I did with 360 above. So, but this time I can't subtract 360, so I'm subtracting 2 pi's. And to subtract 2 pi from this, I'm going to have to find a common denominator. So you can see that's the same as 2 pi. I just subtracted that, looks like 3 times, to finally get it down to 4 pi over 3. And I'm going to use that angle in the 22 pi over 3's place. So to evaluate cosecant of 22 pi over 3, I'm going to be evaluating cosecant of 4 pi over 3. Well, what's cosecant? Cosecant is the reciprocal of sine. And since sine is y over r, cosecant becomes r over y. And again, r is 1. So all I'm doing is flipping the y coordinate. So go find the y coordinate. You can write it like this if you want, but I would rather you just take the y coordinate, flip it, and then again, rationalize with root 3 over 3, and there you go. And that is how you're going to evaluate all of your trig functions. But you have to learn the trig functions in terms of x, y, and r. So remember, what's terribly, terribly important for you is to know these definitions. Now remember, if it's not a unit circle, angle, or if it's just some randomly drawn triangle, these are the definitions of your trig functions. Don't forget those. But if you can use your unit circle to help you, if you're going to do that, well, then the coordinates right here, the r value is always 1. So only when you're using the unit circle can you kind of ignore r or just plug a 1 in its place. But you're going to be using the unit circle a lot. This is great to know, and I think you'll be in great shape if you can get the unit circle memorized, which I'm going to show you some tricks right now, and then understand this process of applying it. Okay, last thing. So how do you memorize this thing? Well, hopefully you're pretty good with the angles. Remember that you're starting at 0 here, and if you skip those middle ones, I call them the middle ones, the ones that are like 45 and 135 and 225, the ones that end in a 5. If you skip those, you're just counting by 30s. So 30, 60, 90, 120, 150, 180, 210, 240, 270, 300, 330, 360. Okay, and then if you go back to the middle ones, hopefully those aren't too bad. You're counting by 45s. 45, again 90. Another 45 is 135. Another 45 is 180. 225, 270, 315, 360. Now, and hopefully you're pretty good on the coordinates. Remember, you're either moving all the way 1 up and down nothing, or you're going up over nothing and up 1, something like that, or it's going to be a combination of these numbers right here, either the root 3 over 2 with the half, or vice versa, or the root 2 over 2 with itself. Same. So hopefully we're good on going, hey, look, I went over a lot, up a little, over a lot, up a little. Same amount, same number, same number. over a little, up a lot, over a little, up a lot. So hopefully you're okay filling out those coordinates with that kind of thinking. So the last thing is, how can I memorize these radian values? Well, I've noticed some patterns. If I look at all of the coordinates, starting with the top and the bottom, I notice that, not even starting with the top and bottom. If I look at every one, every single one has a pi in it. In the numerator, notice the numerator has a pi in every single one of these, with the exception of maybe where I begin with 0 radians. But even then you could argue it's 2 pi radians, and that's a pi in the numerator. Okay? Notice that other than left at 180 and right here at 2 pi, all of the radian values are fractions. So if you begin by just making a fraction for every radian value up here and every radian value down here and putting a pi in the numerator, it's a great start. Now, let's look at denominators. Notice the denominator straight up and straight down is a 2. And then as you move to the right and left, 3, 4, 6. So looking at the denominators, 2, 3, 4, 6. Same on the top. 2, 3, 4, 6. Now don't make the mistake of going 2, 3, 4, 5, but 2, 3, 4, 6, coming down from the top, 2, 3, 4, 6. Now, numerators. Notice every numerator in the first quadrant has a 1 with the pi. So you don't have to do anything. You're already done with those. Every numerator in the second quadrant is 1 less than the denominator. 6 to 5, 4 to 3, 3 to 2. Every numerator in the third quadrant is 1 more than the denominator. 3 to 4, 4 to 5, 6 to 7. And then every numerator in the fourth quadrant is double the bottom minus 1. Double the bottom minus 1, double the bottom minus 1. And then if you're wondering like, well, what about straight up? Since it's not really in the first or the second, which rule do I use? Do I use the rules for the first or for the second? And my answer is yes. You can either use the rule for the first, which says just put a 1 by it, or you can go 1 less than the denominator. Works for both. Same thing here. I can either say it's 1 more than the denominator, like the third quadrant always is, or I could say double the bottom minus 1, like the fourth quadrant. So that should give you kind of a nice, neat way to kind of fill out your unit circle, and then once you have it filled out, you can use it. You could just sketch it out on a test or whatever, and then use it to answer questions like tangent of 20 or cosine of 150 or whatever. All right? Okay, last couple things. I know I've been a little long-winded, but I really wanted to slow down with that unit circle and help you with it. It's pretty fundamental. A couple little things that are going to possibly show up on your homework tonight or moving forward, and it's something I just kind of want to talk about real quickly, and that is when you're dealing with trig functions, whether you're dealing with sine of 52 or tangent of 160 or secant of 512, one thing that you can know real quickly is whether or not your ratio is positive or negative. Like for instance, if I were to ask you something like sine of 42 degrees. Now you know that 42 degrees is probably somewhere right in here in between 0 degrees and 90 degrees, right? And I think everybody will kind of agree with that. That's ballpark a 42 degree angle. Well, if I were to ask you for the sine of that, the sine of that is going to be using this opposite side, right? Which you know is positive because you're going up. And it's also using the radius right here, or the r value, which is always positive, by the way, because it's a result of this movement and the Pythagorean theorem. So this is always positive, this is positive, and this is positive. Well, of course, sine of that angle, because it's going to use the opposite and the hypotenuse, or the y and the r, is going to end up being a positive value, because pluses over plus give me pluses. Well, if you start thinking about that, so is the cosine of that angle. The cosine uses this over this, the adjacent over the hypotenuse, or the x over the r. Again, two positive values. It's going to be positive. Well, so is tangent. Tangent of 42 uses opposites and adjacents, or y's over x's. Those are going to be positive. In fact, all of the trig functions are going to be positive. Why? Because they all used positive movements. Okay? So all of the 6 trig functions, if I'm taking a trig function of an angle in that first quadrant, all are positive. Positive. Sorry. Okay. Now, if I'm in this quadrant, which is between 90 and 180, if you think about it, all the angles over here, and I'm just going to randomly pick something like, how about 115 degrees? So 115 degrees might look something like, oh, I don't know, maybe something like an angle like this. Okay, so it would be all the way over to here. But an angle in this quadrant, even though that's my angle, I can think about trig using this triangle. Okay, now, if I'm moving this way, that creates an x value that's negative, right? Your x value is going to have a negative movement. Now, the y is going up, the y value, that's still positive. Okay, and again, r is always positive. R is always positive. So on this one, any trig function that uses an x will be taking a negative and putting it with a positive, won't it? And negatives with positives give me negatives. So for instance, if I were to say something like, what is the tangent of, say, 115? Well, the tangent of 115 takes the y value and puts it over the x value. Well, we see the y value is positive, the x value is negative. What happens when I put a positive value over a negative value? I get a negative. Okay? Now, tangent and cotangent are the ones that use y's and x's and y's. But what trig functions would be positive here? Well, the only ones that would be positive are the ones that use the plus and the plus. Well, what trig functions use y's and r's? Or r's and y's? Well, that would be sine and its reciprocal cosecant. Sine is y over r, cosecant is r over y. So for this quadrant, let me just scribble that out for us. For this, sine of any angle and cosecant of any angle in that quadrant end up being positive. All the rest are going to be negative because all the other ones include an x value. Think about it. Every other trig function will have an x value in it, and it will create a negative. Now, when you get down to angles like in this quadrant, like let's just say I'm talking about 220 degrees. Okay, so 220. Okay, well, if you think about it, to move along in this direction right here, now granted, 220 would be that angle right there, but I can represent it with this triangle. This is, again, a negative x movement, right? Negative x. So x would be less than 0. But what about y? Y also, because it's going down, would also be less than 0. Now, r is positive, right? Because r is always positive. Let me get rid of that. So since r is positive, I got to think, well, when would I have a negative? Well, anytime I put a negative with a positive, I get a negative. That negative with a positive would give me a negative. Well, the only way I can get positives here are to put negatives with negatives. So here, if I put two negatives together, which I do with tangent, when you think about it, tangent of an angle is y over r. That'd be negative over negative. That's going to give me a positive. And it's reciprocal, cotangent, x over y. So tangent of an angle and cotangent of an angle, they are positive in this quadrant, in the third right here. And then finally, think about a triangle over here. It doesn't really matter the angle at this point. A triangle over here. Again, I have a positive movement, so my x value is positive, but I have a negative going down. My y values are negative. And again, my r values are always positive. So what's the only way to get a positive here? To have trig functions with x and r. Which ones have x and r? Cosine is x over r, and secant of an angle would be r over x. Those are going to be positive here. Well, I've just explained all this, but a better way to think about it is a little shortcut we learned, and it looks like this. If you ever want to know where trig functions are positive, all of them are positive in the first quadrant. Sine, we said, and its reciprocal cosecant, those are positive in the second. Tangent and cotangent of angles, they're positive in the third. And then finally in the fourth, we said cosine and secant. Well, the way I remember it is all students take classes, which is really ironic given what we're doing right now, but I guess technically this is an online class. So all students take classes, and if you think about that, that will immediately let you know, for instance, if I were to say, hey, is tangent of 112, is that positive or negative? Well, since 112 lands right here, the only trig functions that are positive there are sine and cosecant, so it must be less than 0. If I were to say, hey, cosecant of 227, is that a positive or negative value? And you go, well, 227 is somewhere between 180 and 270. Cosecant, well, the only two that are positive are cotangent and tangent, so it must be negative. Okay? If I were to say something like cosine of 318, positive or negative? Well, 318 somewhere between 270 and 360. So if it's in this quadrant, the only ones that are positive there are cosine and secant, so that must be positive. So that's some insight that will come up and be useful later, but I remember it as being all students take classes, all being all the trig functions, students being sine, take being tangent, classes being cosine, and then of course the reciprocals that go with them because it's the same letters. All right? So let me give you a quick last minute problem and we'll call it quits for today. You can do the best you can with your homework, and then if you have any issues, you can always email me or email a friend or text me, and I'll do the best I can to communicate it back. Okay? So real quickly, what if I get, and watch how this plays off in the math that we're doing. So what if my question to you was this? Determine the 6 trig functions of an angle in standard position going through the point let's go with we'll make it easy, -3, 5. That's not super easy, but whatever. So if you think about the image of this, if I have a movement of left 3 and up 5, I would be over there in the second quadrant. So if I go left 3 and then up 5, there's my point. Now remember what standard position means. Standard position means my angle is going to be pointing, one arm is going to be pointing at 0, and the other arm has to go through this point. Okay? Now technically that is my angle. All right, so I'm doing the 6 trig functions of that angle. I want to know what is the sine of that, the cosine, the tangent, the cotangent, the secant, and the cosecant. I want to know that. Okay, and remember, I know that the sine is y over r, cosine is x over r, tangents y over x. Got to have these memorized. Cotangent's the reciprocal of tangent. Secant's the reciprocal of cosine, and cosecant's the reciprocal of sine. And you'll notice I'm putting the r's in there because I'm not using a unit circle angle here. Okay? At least maybe I am, but I don't know that I am. All right, now I have to draw a triangle from this angle. So I'm not going to draw the triangle like this. Don't do that. Okay? You always draw this perpendicular down to the x-axis, and we're going to let this represent that angle. But I have to remember to include things that are important. So my x movement to get to here was -3. My y movement was 5. And what can I do to find this r value? Pythagorean theorem. So I'm going to come over here and say, all right, the r squared equals the x squared plus the y squared equal 9 plus 25. So I take the root of that r, and I get plus or minus root 34, but we know r is always positive, so we're going to keep the positive value. That becomes a root 34. Now from these, I just fill in my trig functions. So the sine, 5 over the square root of 34, I rationalize 5 root 34 over 34. Cosine, -3 over the root 34, and I get -3 root 34 over 34. Tangents, the y over the x, 5 over the -3, and we know to never leave a negative on the bottom, so -5/3. Cotangent's the reciprocal of sine, so -3/5. Secant is the reciprocal of cosine, so I'm going to flip this value, and I get negative root 34 over 3, again putting the negative out to the side or on top. And then the cosecant is the reciprocal of sine, or you can use those values, but I'm just going to take those, and since I've already done the math and the work, root 34 over the 5. And those are my 6 trig functions of an angle going through that coordinate. And hopefully that will be helpful. All right, very last thing, probably said that twice, and I will definitely try to streamline these lessons in the future. But the last thing I want to talk about is a reference angle. Okay, so a reference angle, that's how you spell reference angle. A reference angle is defined as this. It is the acute angle formed by the terminal side of an angle in standard position. I'll illustrate this in a second. And this is what's key, and the x-axis. Now the key is acute angle, all right? So let's just think about random angles. Like what if I'll give you 3 random angles, all right? Maybe I'll give you 4. So first one, what if I gave you this angle right here and told you it was 71 degrees? Well, according to this, it's the acute angle formed by the terminal side of an angle in standard position. Now remember, standard position, they got one arm's got to be pointing at 0, and then the other ray is somewhere else. So if this is 71 degrees, what would be the acute angle formed by the terminal side and the x-axis? Well, it's not that. That's not acute. So it would have to be this. So in this case, the reference angle is also the same as the angle itself. Now, what if the angle's over here? Like this one, let's just say it is 118 degrees. Okay? Well, again, angle in standard position. So if this is at 118, I want the acute angle formed by the terminal side and the x-axis. Well, that's not acute. This would have to be acute. So how do I figure out what that measure is right there? Well, remember, if the whole thing is 180, I can take 180 and subtract that 118. So the reference angle right here, I'll call that theta, reference angle. So the reference angle here, I'm just going to go 180 minus that 118, and I end up with 62 degrees. And if I mess the math up a little bit, cut me some slack. But that means the reference angle, this little bitty angle right there, would be 62 degrees. Now, if it's down here, say in this quadrant, let's just say that was, I don't know, 213, okay? Well, again, in standard position, so one ray's got to point at 0, that would be my 213. But if I want the angle, acute angle formed by the terminal side and the x-axis, I don't want that. And don't take it to the y-axis ever. Don't ever find that one. That doesn't even have a name. It's always the x-axis. So that would be this angle right here. So how do I find that reference angle right there? Well, if it's 180 to here, and this is at 213, it looks like I went past 180, 33 degrees. So how do I find, that's how I did it there. How do I find a reference angle in the third quadrant? Well, I'm just going to take that 213, subtract off the 180, and that's going to leave me with 33 degrees. So that little bitty angle right there is 33. And then finally, in the fourth quadrant, if you have any angles there, let's just say it was, I don't know, 294. Okay, so again, here's 0. 294 would be all the way around to there. Well, how do I find the reference angle? Well, it's the terminal side, x-axis, not this. Don't go to the y-axis, always the x. So that right there is my reference angle. How do I find it? Well, if the entire way around is 360 and this is 294, it seems like I could take that 360 and subtract off the rest of that to get what's left right here. So again, to find the reference angle in the fourth quadrant, I would just take 360, subtract off that 294, all right, and that's going to leave me with 66 degrees. So again, you'll notice on all of these, the reference angle always ends up being an acute angle. And if you follow that consistently, you should be in pretty good shape with your homework. All right, guys, good luck.